Yeah, sorry, today is Valentine's Day. I should cancel today's class. I'm very sorry. So last week we reviewed the PCA and we compared the factor analysis and the PCA. And today we're gonna look for the new topic. Okay, EFA, exploratory factor analysis. This part, can you see it?
Nope, not at all.
Sorry. So we're gonna, introduction to this topic, including some objectives for how we're going to use EFA and how to conduct, EFA. The first important thing is the number of factors. I will show you how many methods. Okay, I will show you at least 4 methods to decide number of factors. This is the most important step for EFA. So you have to decide. Okay, so suppose I have 20 items, then you have to decide how many items you're gonna use. I'm sorry, not how many items, how many factors you're gonna use. And then we're gonna look at the parameter estimation. So how are we going to decide the lambda values, the coefficients, or the field size, okay, and the factor rotations. How to rotate. Welcome. How to rotate those factors to provide a better interpretation of our factor analysis. And then we're gonna look at the factor scores. Okay, some people focus on this part, factor scores, because we cannot observe those values. We hope that we know the latent values, but actually this is not our focus. Okay, although some people look forward to get those scores, but those are not our focus. I will show you why. Okay, and how to do the interpretation. How are you going to explain the factor structure, the pattern of those factors? And session 2, we're gonna have a lab. Okay, so before look at those example, we will talk about some practical issues. For example, sample size. Some people ask me, okay, so I'm gonna collect data for today's for this semester, but I don't know what's the sample size. So I will give you some guidance, but not very, there's no threshold, there's no rule of thumb to, okay, so what structure, how many factors, how many items, but I will provide you some just guidance to help you to decide your sample size. And of course, we will have lab, and we use different software to do the practice. Yeah, this is a review. Previously, we talked about the goal of EFA. So we're gonna study the dimensionality of a bunch of items, a lot of variables. We're trying to reduce their dimension, okay, the number of values. So we will have EFA and CFA. Okay, EFA. So what is EFA? Exploratory. Okay, so we're trying to do some exploratory factor analysis. So we're trying to discover something. So it's one type of factor analysis. So this is our goal, trying to discover the pattern, okay, the nature of the underlying structure of a lot of responses, outcomes, variables. Okay, so that's our goal. So we do that by focusing our correlations or covariance structure. So we're gonna look at the correlation matrix or covariance matrix. Okay, and then do the discovery. It specifies the number of latent variables. Okay, but in EFA we don't have any structure. We're just trying to find the pattern. For CFA, we do have structure. So EFA, no structure on the linear relationship. So these are our objectives. As I mentioned, this is the most important goal for EFA. To decide the K. K is the number of common factors which influence a set of respondent. Okay, so this is the K, number of factors, number of common factors. Of course, we have unique factors, so that's not our focus. And then we're gonna look at the coefficient, okay, or the strength, or the loading. So which decide the lambda factor, the lambda matrix. So we have a big matrix, lambda matrix. if we have P variables, observed variables, it's P by K, okay? P observed variables, K latent factors. So this lambda matrix is huge. P by K items, elements inside this matrix. It connects each factor and each observed variable, okay, to try to look at the coefficient. And then we can also check the factor scores, the F scores. So those are our primary objectives. We're gonna do all of these today. Oh, these are other objectives. So these are our primary objectives. So of course we have some other important objectives. For example, we're gonna reduce, okay, the number of variables, as I mentioned, as I repeated again and again. Okay, so we're trying to make the large number of variables to smaller number of factors. And we can use EFA to establish that some tests actually measures the same factor. So we can see, okay, so which factors are measuring the same factor. So by looking at the factor pattern. And then we can also validate the scale or index by demonstrating that its item load on the same factor, the same as the previous objective. Okay, so we're gonna discover the pattern, the structure. Also, we can validate the dropping some proposed scale items which cross-loading on more than one factor. So sometimes you have a really good questionnaire, but after you run EFA, you can figure out, okay, maybe this item is not well designed. I'm gonna drop it. Why? Because you look at those factor loadings, you have some cross load. So I will show you what is the cross loading. So theoretically, okay, ideally, we're trying to get some factors which gonna influence some specific items, but sometimes we have some cross loading. Okay, so we have not very ideal pattern. It's allowed, but it's not the best. Sometimes we're gonna leave those items because those items maybe it's really important for our test. But sometimes we can just drop them. Okay, it's up to our structure and also up to your goal. Okay, so we will have some examples of this. I'm sorry, this part. Yeah, just please look at the slides on our desktop. This part is really right. We can also select a subset, okay, a subset of variables from a larger set based on which original variables have the highest correlation with some F factors. Of course, we're gonna take some really important variables or items from a large questionnaire, from a large item pool, okay. And we can create a set of factors which will be treated as uncorrelated variables. Okay, so this is important. Sometimes we're gonna assume the factors are independent, okay, uncorrelated. Then we have two types of factor structures. It's orthogonal and oblique. Okay, so sometimes we allow the correlations are can be between these factors, but sometimes we're gonna assume that these are independent, uncorrelated. In this case, we can just deal with the multicollinearity. And I list other objectives. Okay, all of these are our goals to identify the nature of the construct underlying responses in a specific area. Okay, this is also very important. What sets of items came together in a questionnaire? Of course, yeah, we're gonna group those correlated items together. Okay, and then to demonstrate the dimensionality of a measurement scale. Okay, so because researchers often wish to develop scales that respond to single characteristics. Okay, so sometimes we're gonna pick some very highly correlated items, and then just decide that those are indicators of some specific single vector. To determine what features are the most important when classifying a group of items. To generate the vector scores representing values of the underlying construct for use in another analysis. Yeah, this is important, but actually some people argued on this. So some people just don't agree of this part. Okay, so they said, okay, vector scores actually is, what can I say that? Vector scores can be have a lot of solutions. Again, if you want to use them, you have to identify those models, and also you put a lot of assumptions, and then you can decide the vector scores. We have different methods. I will show you different methods to decide to get those vector scores. But in most cases, people don't just recommend this method. Okay, so I just list all of this background. Okay, our objectives of EFA. So it's widely used, and it's very, maybe it's very, it's the most popular way to figure out the items. So EFA, we're gonna cover all of these topics today. The first goal, decide the K. So we have two main approaches. Eigen decomposition is very important. Okay, so of course, inside this approach, we have different methods. I will show you 3 methods at least. But people discovered that this method maybe it's not very good. And then we're gonna use parallel analysis. Okay, parallel analysis, eigen decompositions. These are 2 kind of like approaches. Okay. And for estimation, okay, how are we going to decide the lambda? Again, we have 2 main approaches. The first one is still eigen decomposition. So that's why the eigen decomposition is extremely important to do the vector analysis. We can also use maximum likelihood estimation methods, okay, different ways to do the estimation. Vector rotations. I just listed 3 here, but actually there are a bunch of these, okay, a bunch of these rotation methods. Varimax, Promax, geomean, okay, so we have a lot of others. So these are very popular rotation methods. Vector score estimations, we can use regression method, we can use borrowed methods, and how are we going to do the interpretation? Yeah, so these are our main goals, okay? How to select the K. How to rotate your factors, okay, to get a better interpretation. And how to do the interpretation. Okay, let's look at the first goal. The first target we're trying to achieve today, determine the number of factors. Let's look at the first approach by using the traditional eigen decomposition analysis. First step, okay, you're gonna do eigen decomposition, eigenvalue analysis based on the, okay, sometimes we focus on their correlation matrix, sometimes we focus on their covariance matrix. So correlation matrix is the most popular one. We just, based on that matrix, we do the eigen decomposition. And then you get the eigenvalues, as I mentioned. So last week, I gave you example. So we have 2 by 2 matrix. So we figure out we have 2 eigenvalues. The biggest one is 3. The second one is 1. So by using that way, we can figure out all eigenvalues for that matrix. And then we pick, so we choose the all eigenvalues which are larger than 1. So just count how many of our eigenvalues are larger than 1. That number is our number of factor. Okay, so suppose, okay, the p-value, okay, suppose I have 8. I have 8 items. So basically, I have 8 eigenvalues. Okay. 8 eigenvalues. The biggest one suppose is 3. The second one is 1. 1.1 suppose. And then the rest of the eigenvalues are 0.03, 0.001. Then we just keep 2 because 3 and 1.1 is larger than 1. So by using that way, we decide the number of factors. So this method is called a Kaiser's rule, okay? Or Kaiser's criterion. So it's very simple, and it's very, very, very popular. Maybe it's the most popular way to decide the K, okay? And by default, in most software, they just use this method. So we just drop all components with eigenvalues under less than 1. Okay. But you know what? Although it's very popular, but it's not recommended because people figure out that that number tends to over extract factors. Okay. So people think that, oh, maybe we're gonna figure out other method. So we have another method which based on eigen decomposition again. The same first step, do the eigen decomposition of the matrix, correlation matrix or covariance matrix, and then rank. Just like the first method, okay, we rank eigenvalues from the largest one to the smallest. And you're gonna calculate the cumulative, okay, cumulative eigenvalues. So suppose the biggest one is 3, the second one is 2, and the third one is 1. Okay, so we have a bunch of eigenvalues. Just calculate the cumulative eigenvalues. The first one, 3. Second one, okay, 3 by plus 2. Now we have 5. Third cumulative value is, okay, 3 plus 2 plus 1. Now we have 6. And then we just count, we just calculate the percentage of the total variance. So we take cumulative eigenvalues accounted for 80% of the total variance. Okay. So if we reach 80% from the biggest one to the largest one, if the cumulative eigenvalues reach 80%, then we just stop. Okay. So the remaining eigenvalues we just drop those, and then that number is the number of factors. So this is another way. Okay. The third method, I don't want to do any calculation. Okay, I just want to look at the plot. This plot, okay, this actually, I'm sorry. Please look at your slides in your desktop. So we have a lot of dots here. These dots are actually our eigenvalues from the largest one to the smallest one. Okay, so suppose this is the largest one, more than 6. And then we have another one here. It's around 2, less than 2. It's around here. And then we have another one here. Okay, it's around 1.5. And we have another one. And then we have a bunch of small dots here. And then we just use dots and a line to create a plot. This plot is called Patel's-Cree plot. I'm sorry, Patel's-Cree plot, okay. And then we can see that, okay, from the biggest one to the smallest one, we have something, let's drop here, okay. So from here to here, from the biggest one to the fourth one, it seems that it's dramatically bigger than the remaining eigenvalues. All of these are quite similar. Okay. And then from here to here, it seems that the drop is big. So we just decided to use a cutoff point here around here. We decided that we have 4 eigenvalues, which is dramatically larger than the rest of eigenvalues. So the K is 4. 1, 2, 3, 4. So So this is called the Cattell-free plot. So those are three methods by using the eigendecomposition. Simply just check the eigenvalues and compare them to one. Okay, as a rule. The second method use a cumulative eigenvalues, and we just calculate the 80%. Okay, and the third one just look at the plot. We don't have any. So that is key. All of these are based on the eigendecomposition, but people argue that this method is not the best one. So we have a new modern analysis called a parallel analysis. Parallel analysis. What's parallel analysis? Okay. So this method is recommended. It's strongly recommended. It's Monte Carlo method. So what should we do? Actually, we just simulate, we just generate a lot of data. It's Monte Carlo, okay, Monte Carlo that we manually generate a lot of data and do some calculation. This is a detailed procedure. First step, I'm gonna generate, of course, I ask my code, okay, my R or other software. I will show you the code. And then you can just look at the code and understand these detailed steps. Generate B sets of random data. B. Usually this B is a large number, okay, 1,000 or even more. Okay, B sets of random data. So all the data are random. There's no actual structure with the same dimension as original data. Suppose, okay, I have original dimension. Okay, I have 8 variables. Okay. I have a lot of this. So you just generate the data with the same dimension, but all the numbers inside that generated the data matrix is random. Okay. So those data are called parallel data or parallel samples. Okay. For each data, okay, once we generate one data set, we can have their correlation matrix. And for that matrix, we calculate the eigenvalues. For that specific newly generated matrix, we calculate that eigenvalues. And we have B sets of random data. So for each of these B, we have one set of eigenvalues. So we're gonna calculate the average of eigenvalues from the all B sets of eigenvalues. Suppose I have B means suppose I have 1,000. For each of these 1,000 data set, I have a specific random matrix, okay, random correlation matrix. And I have one set of eigenvalues. So after I got 1,000 sets of eigenvalues, I just calculate the average. The average of the biggest eigenvalues, the average of the second biggest eigenvalue. So we just get the average. And then we're going to compare the original eigenvalues with the average eigenvalues. So the average of B, 1,000 sets of eigenvalues is kind of like treated as our baseline because these are generated from our noise, random. We don't have any special structure on those random data. So these are kind of like our white noise. We compare our original eigenvalues with the white noise. If the eigenvalue is specific, okay, dramatically larger than the white noise, then we think that okay, that eigenvalue is so specific. That's indicated that we have some special factor influence that. Okay, so for a factor that is not because of noise, its eigenvalue should be larger than the average one from the random data. So the idea or the logic is that we have original data sets. we're gonna compare the original data sets with some noise. But how are we going to get those noise? We basically generated them. We generate a large number of data sets. For each of that set, we have P eigenvalues. Suppose the dimension of the original data set is P, okay? So we have P from the largest one, lambda 1, lambda 2 to lambda P. That is for the first generated random data. For the second generated data, we have lambda 1, lambda 2, lambda 2, lambda P. For the third generated data, we have lambda 1, lambda 2 to lambda P. And then we have 1,000 lambda 1, we have 1,000 lambda P, lambda 2, we have 1,000 lambda P. We got this average. So we have the average lambda 1, average lambda 2, average lambda P. And then that will be treated as our noise, okay? And then we're gonna compare the original eigenvalue with this generated kind of like a noise eigenvalues. If the original eigenvalues are larger than the generated eigenvalues, we think, okay, there might be something special. There must be some special, it's not due to noise, due to some latent factors. By using this method, we just decide the number of the factors, okay? That is the logic. So I also give you some plots, and again, this plot will be generated by our R code. I will deal with the R code of the parallel analysis. Okay. So we have, this is our original eigenvalue. Okay, we have 6 here, we have almost 2 here, we have 2 around the 1.5, and we have a lot of eigenvalues here. And then we generated a lot of like noise random data. So we have 2 lines here. Actually, we have the average line, the dotted one. This is average. Okay, it's the average line. We also have up bound, 95%. The dashed line, up bound. And the black solid line is the original data. So we're gonna compare this line with the average here. So this is due to noise. This part due to noise. So by doing the comparison, we decided that maybe 1, 2, 3, 4. These 4 are larger than these 2 lines. It can be average line, it can be up bound. Okay, it's up to you. So we're gonna decide that we have 4 latent factors, but not these. Okay, these are obviously lower than the average line. So these are due to noise. We just discussed. We just discussed these eigenvalues. We decided these 4. Okay. So the final result, I just introduced the 4 methods to decide the K. The final answer makes the same. Okay. So if you look at the Kaiser's rule, we have 1, 2, 3, 4. Okay, 4 eigenvalues are larger than 1. Okay, if you use a cutoff point of 1 here. Okay. So we determine the K is 4. Cumulative, we didn't get the cumulative, but you can do that, maybe it's 4, okay? And the split plot, you can also decide that it's 4. By parallel analysis, it's 4. So the final answer, the K, for the K might be the same, but the methods are totally different. Of course, in some cases, in most cases, the K is the same, but in some cases, it might be different. Okay? Suppose if the eigenvalues is around here, okay, here, under the regression, not regression line, under this average line, maybe here. By using the split plot, maybe if it's around here, then maybe you can just ignore these 2. Okay. Wait a minute. So if it's here, then by using the Kaiser's rule, we still have 4 because these 2 are still larger than 1. But if we compare with this average line, we're gonna decide that we only have 2 because these 2 are below this average line. Okay, so in some cases, the K is not the same, but in most cases, the K is the same. Okay, any question about the first step? First step. Yeah, you can just pick any of these methods. The most popular one, just check the eigenvalue and the cumulative eigenvalues and the plot and the parallel analysis. Okay. In our code, okay. Anyway, I will give the detailed code. In R, all of these calculations is very, very simple. We only have one command to get the eigenvalue. Okay. Eigenvalue, eigenvectors, all of these will be very, very simple by using our code. Okay, that's the first task. Okay, done. If you don't have any question, then let's move forward to the estimation method. How are we going to get the parameter estimates? Okay. So again, we're gonna based on the correlation matrix. Okay. In some cases, we use covariance matrix, but in most cases, we use a correlation matrix for EFA. And the first approach, okay, again, we have different approach. The first approach, eigen decomposition or spectral decomposition, just like we mentioned before. We can also use maximum likelihood method. Okay, just look at the first approach. We do the decomposition, okay, by doing the review. So each of you might be familiar with this part, okay? So we have the matrix here, symmetric matrix. It could be correlation matrix or covariance matrix here. And we have eigenvalues, okay? The L is diagonal matrix consisting of those eigenvalues. It's diagonal. From the largest one to the smallest one, we have diagonal matrix here. And we have eigenvector matrix, okay? So the U here is a matrix consisting of a lot of columns, okay? Each column is corresponding eigenvectors, okay? So we have biggest one. So suppose we have the eigenvalue of the matrix lambda. Okay, so we have largest eigenvalue, the second largest eigenvalue, and P eigenvalues, and we have this diagonal matrix. So all of these are 0, 0. Okay. And this we call it L. Okay. In the previous last week review is a document we call it D. Okay, but it's the same. Okay. So this is the eigenvalue matrix. For each eigenvalue, we can calculate that eigenvector. Okay, so based on that eigenvalue, we calculate the eigenvector. So we have U1 here. Okay, and for the second eigenvalue, we calculate the second eigenvector. Okay, so we have U2. Okay. So we have all of these eigenvectors. Okay. Of course, there are a lot of eigenvectors. So we have, if we use make it as unit one, we have one solution. Okay, so by combining all of these U together, we have the U matrix here. Okay, this is the L matrix. The U matrix is all of these columns are eigenvectors U1, U2, U3. Okay. So this matrix is called U. Okay. So we just did the exercise. We can, based on the covariance matrix here, we can calculate the eigenvalues. We can also calculate the eigenvectors. So we can get this decomposition. This is called eigen decomposition. Okay. So the U matrix times the diagonal element, diagonal matrix here, and the transpose. Okay, the transpose of this U matrix. So all of these are known here. Okay. Yeah, so we have L here, we have U here. U here, we just decide that it's orthonormal. So the unit is 1. Okay, it's orthogonal and also the normal or the length is 1. Yeah, orthogonal is 1 more. That's why we can decide the unique solution of U. Otherwise, we can have many U's. U is not unique. This is a decomposition. And then we can rewrite. Okay, so we can rewrite this format. So let's just keep it as there. Okay, so just notation. Some people use T, some people use tail, some people call it lambda. Then we can, okay, so let me just show it here. Okay, so we have U1, and we have lambda L. Okay, L actually is including lambda 1, lambda 2, lambda 3. This is L matrix. So transpose because U1 here, okay, U2 here. So it's transpose. And then we can actually decompose this part. This is a squared lambda 1 and squared. Okay, square root and square root, squared. And the diagonal, okay, diagonal times diagonal elements, we can decompose it into 2 parts. So this actually becomes, if we treat it in 2 parts, okay, lambda, square root of lambda times the square root of lambda. So we combine the first lambda to U and the second square root of lambda to the right side. We can have, okay, so we can have square root of lambda 1, U1, square root of lambda 2, U2. So all of these are transformed. And we can have lambda P, UP. Because it is a post multiplication, okay? So we have the column change. And then we have the other part, square root. And the right side of this transpose of V. So we can have the lambda 1, U1, okay? Lambda 2. Okay, now we try to decompose or not compose. Actually, we just transform. Okay, we just change the format a little bit. We change this original decomposition to this form. Okay, to this form, and we can totally check these 2 are same. Okay, this is just transpose of this original because the lambda are exactly the same. But here we have columns, here we have rows. So this lambda is just transpose of this lambda. If we rename it, okay, if we call this matrix lambda, matrix lambda, then this is just transpose of lambda. Okay. This whole matrix is called lambda, and we have transpose of lambda. So we have this one. Okay. Then this is our new number. So we call the transform the eigenvalue matrix. Okay, U1, U2, I'm sorry, here we use K. I'm sorry, number K. Yeah, it should be, yeah. So we have, I'm sorry, I use different notation. Here we use lambda and here we use L. I'm sorry, I apologize. So it's confusing, but here means it's eigenvalue. This is eigenvector. Okay, eigenvalue square root, eigenvector. So this is lambda. Suppose we have k vectors, so we only have k vectors. And then each element here inside this matrix, we just call it the vector loadings. Okay, so we have the vector loadings. This is the whole matrix, k columns. And the elements here is just the square root of the k. Okay, suppose we have k. This is capital K, the biggest number of suppose we have some k here. And the u is just the element inside of the eigenvector. So this is the vector loading. We just obtained the vector loading by doing the eigen decomposition. This is one method. This is one method to decide the lambda, the eigenvalue here. Okay, not the eigenvalue anymore. This is a vector loading. Okay, this is a vector loadings. This is the whole lambda matrix. That's the lambda matrix in our vector analysis. So the K decided the largest eigenvalues and the corresponding eigenvectors because the K decided based on the first step. Okay, and then we just use that to K. So here we have different columns, and each element is okay. That's a common factors part. But we do have the unique factors part. This is a common factor, the lambda f part. We have y equals lambda times f. We also have the u part, the unique factor part. And that part, this is a unique variance. Okay, the variance of the unique part, psi. Okay, we use psi. Psi has its diagonal matrix. We assume these are independent. So we have the variance of the variable minus, this is the sum of the loadings, okay? And of course, this is the common factors. This is come to the common factors. And we assume that the model part and the sample size part, the diagonal elements is 0. This is sample part, sample variance part. The common factors part, this is a unique variance part. Total, this is a total due to the common factors and also due to the unique variance. Okay, that's the first method. Okay, that's a method to obtain those factor loadings lambda. Okay, just starting from this decomposition. And as I mentioned, we can also estimate those parameters by using the maximum likelihood estimation method. Okay. So we're gonna use a description function of FML again. So we remember this function. Okay. So we have the description function of maximum likelihood. Okay, it's a log of the model-based covariance matrix. Okay, here the model-based covariance matrix is based on the factor model. So do you remember the formula here? For each specific model, we can just derive the capital sigma. Okay, capital sigma actually is totally based on our model. So for mediation, for regression, or factor model, we all derived the capital sigma here. So the capital sigma of the factor model actually is, you still remember the format. This method. In most cases, if we assume there's a phi is identity matrix, then we have this format. Okay. Yeah. So we have it is a function of lambda and also psi. Okay. So this is for factor model. For factor model, we have this form for this form. And for mediation, we have other form. Okay, we calculate. For simple linear regression, we have that. Okay, for model regression, we have different size. So it's model based. This is a model based side. And then take the determinant. Okay, determinant. And then take the log function. And then we have the trace. Okay, this is a trace. And the product of these two matrices. The S is a sample-based covariance matrix. We have to combine the sample covariance matrix and the model-based covariance matrix to try to make these two. The difference is smaller as possible. Again, this is a model-based covariance matrix by including the vectors, loadings, and the sidecar. Okay, this is a sample covariance matrix. Okay, the product of these two. This is inverse of the covariance matrix times the S, and the whole product takes a trace. And then we need to minus the log of the determinant of the sample covariance matrix, and minus the P. Okay. This is the P is the number of variables. Okay, this is the FML. So by looking at this target function, dispersion function, we can try to minimize that function, okay, and then get the parameter estimate of lambda and the psi. Okay, these are parameters. All of these are parameters. So basically, you're gonna get the first derivative of all of these parameters. That's a huge equation, okay, and also this get the first derivative based on these elements of psi, and then also make sure the second derivatives are positive, and then we get the solution, and we have the elements estimates, the parameter estimates. Of course, all the computer can help you to do that. Okay, if you're trying to maximize or minimize, we can use a lot of numerical ways to get the optimal solution. So that's another way to get the estimate of factor, not factor, model parameters. Okay, that is the model parameters. We can use a identity composition or maximum likelihood estimation. Any question? Okay, of course we can have some other methods, but these are two main methods. Okay. Next, let's look at the model identification. As I mentioned, okay, so in fact analysis, a lot of solutions are not unique. We may have different solutions. That's why we need to do model identification. So why it's not unique? This is a example. Suppose we have this solution. Okay, so we have lambda matrix here, and the transpose of lambda and the psi. Okay, by assuming the phase are linear matrix. So this is one solution. Okay, we have lambda here, we have psi here. Now we assume we have some orthogonal matrix T. Because it's orthogonal, we have this property. Okay, so we have this T equation T times the transpose of T is a linear matrix. That is due to its orthogonal matrix. Then this is kind of like a linear matrix. We replace the linear matrix with a T times the transpose of T. Now, once we have this form, we can generate another new lambda. How? We can combine these two, lambda T, we can combine these two together. And the T transpose times lambda transpose, looking at, think about the transpose rules. This is just a lambda T transpose, okay? This is the rule of the transpose. So we have something here times something transpose plus a sigma. So this can be a new solution of capital sigma. We can use star, okay? This is a lambda star. Lambda star is here times the transpose of this lambda star plus I. So look at this form. The lambda and the lambda star satisfy this equation, make this equation hold. So lambda and the lambda star are all solutions of this equation, okay? And of course, you can create a lot of like T. So you can have a lot of like solutions. So the solution is not unique. Okay, so this is a new solution. This is also satisfy this equation, make this equation hold. So the new one is the original one times the T here. So if you, once you find the unlimited T, then the solution will be unlimited. Then we're gonna add some constraint to make the unique, to make the solution unique. Okay, so we can have many constraints, but this is also a very popular one. Okay, we can make this one's diagonal matrix. The solution, okay, the one solution lambda, the transpose, the inverse of the psi times the original lambda, make this product, okay, diagonal matrix. Once we have this constraint, then unique becomes unique. Of course, you can change the constraint, okay? And this is just one of them. So it's model identification. Now let's calculate the degrees of freedom again. Previously, in last semester, we calculated the degrees of freedom for simple linear regression, for multiple regression, for moderation, mediation. Okay. For factor models, this is a way to calculate the degrees of freedom. And again, we have P. Suppose we have P observed variables. And then the K is the number of factors. Okay, K is less than P. Okay, K is less than the number of observed variables. What is the number of information? This part is the same. From last semester, SEM1, we know the number of information is calculated by this equation, okay, by this formula. P times P plus 1 divided by 2. If P is 2, that means if we have two variables, X and Y, then, okay, 2 times 3 divided by 2 is 3. We have 3 pieces of information. We have variance of X, we have variance of Y, we have covariance between X and Y. That's it. We have 3 pieces of information. If P is 1, if we only have one variable, one X, then 1 times 2 divided by 2, 1. So we only have one piece of information, which is variance of that variable. That's it. If P is 3, 3 times 4 divided by 2, 6. We have 6 pieces of information available for us. Suppose, okay, 3 variables, when P is 3, then X, Y, Z. Then we have variance of X, variance of Y, variance of Z, covariance between X and Y, covariance between X and Z, covariance between Y and Z, 6. That's a maximum number of information we can use, okay? So that's a number of information. And then, for factor model, how are we going to decide the number of parameters, okay? This is number of parameters. Okay, this is number of parameters. Why do we have this number? Okay, why do we have this number of parameters? So think about the parameter factor model. So actually we have, okay, lambda. So think about that. We have the sigma is, okay. So this is the formula for capital sigma. We have a lot of lambda inside the factor loading. So suppose we have P variables. We have K number of factors. So this is a P by P. This capital sigma is P by P. This matrix is P by K, okay? So suppose we have K number of elements. And this is the covers of factors. So the dimension of this is P by K, okay? And this is K by P because this is transpose, okay? So we can cancel the P, K, K here, K, K here. The fact that we have P by P here. And this is also P by P. This is diagonal because we assume that the unique factors are independent. So we have diagonal side here. All of these are unknown. All of these are unknown. We don't know the lambda value. We don't know the factor scores. We don't know the three elements. We don't know the size scores. All of these elements are parameters. So how many parameters? Okay, number of parameters. How many parameters inside this part? We can just calculate that, okay? For lambda, we need to know all elements. All of this lambda 1, lambda 1, 2, all of this one, lambda 1, P, okay, lambda P1, lambda PK, lambda PK. All of these elements need to be figured out. So we have P by K, P times K elements. These are unknown parameters. And then for this side, for this phi, it's symmetric. It's correct matrix of the factors. So we have K by K matrix. So how many elements inside here? Because it's symmetric. Okay, so the elements here is K plus K, K times K plus 1 divided by 2. Okay, this is the parameter, number of parameters inside the phi. Okay. And of course, we have lambda. Lambda, we have already calculated here. And then we have psi. Psi is diagonal. Okay, we have P by P, diagonal. We needed to know P elements. So that's why we have P here. Okay. But we needed to minus something because we need to identify our model. We put some constraint. So we assume that we use that part. Okay, we assume we put this as our constraint. And the lambda actually is P by K, so P by K. The inverse of the psi is P by P, okay? Transpose is K by P. So we have, finally, we have K by K here. So we're gonna assume this is constrained for that unique solution. So we need to put a K square elements constraint here. So that's why we need to minus the K square. So totally we have this number of parameters. So number of information minus number of parameters is a degrees of freedom. So just do the calculation, do the algebra. Okay, this number minus this number. Do the calculation. So finally you have this number. Okay, P minus K squared plus, minus P plus K, and then the whole part divided by 2. So the P should be larger than K. P is number of variables, okay? It's number of variables, the number of items here, okay? K is number of factors. So this number definitely needed to be less than the P, okay? So K should be less than P. So this is the degrees of freedom of the second model. Yeah, K should be chosen such that this number, the degrees of freedom are larger than 0. Okay, of course, if it's less than 0, then it's not easy to get computation. So that's for factor model. That's it. This is the degrees of freedom. Any question? Questions so far? Okay. And then let's look at the factor rotations. Okay, so we may have different factors, and we can just change the x-axis and the y-axis to have better scores, to have better factor scores. This is gonna help us to interpret, to do the interpretation, okay? Because by changing those x-axis or y-axis, it's gonna help us, okay, how to name, okay, how to understand those numbers, how to understand those factors. So the only goal to do the factor rotation is to get a better interpretation of factors. That's our only goal, okay? We're trying to clearly explain the factor scores, factor patterns. And of course, we have a lot of like rotation methods. We can have orthogonal rotation, we can have oblique rotation. Yeah, so these are just some of them. Varimax rotation, convex rotation, quadrimax rotation, equimax rotation, oblique rotation. Also. They have different roles. Okay, for each type of rotation, they have different roles. Maximum sum value or minimum sum value. Okay, so I'm trying to make the factors look better. Okay. Yeah, so rotation serves to make the output more understandable and is usually necessary to facilitate the interpretation of factors. I will give this example. Okay, by using different rotations, you can do the comparison. Okay, so for some method, the pattern, the factor pattern is much better than the other one. So we're gonna pick the best pattern by using different rotations. Yeah. So this part is just theoretical introduction. So we will have the demonstration. Yeah, we can. For example, in this case, this is not good interpretation. So we're trying to have this case. Okay, so from here to here, all the dots. Okay, if you have this factor rotation, all the dots located on factor 2, all the dots are located on factor 1. So you can explain that. Okay, this can be explained by factor 1. This can be explained by factor 2. But if you use original one, so this can be partly explained by factor 2, partly explained by factor 1. Okay, it's not very clear. And these dots can be explained mainly by factor 1, but some by factor 2. So this is much better than the interpretation of this factor structure is much better than this one. Okay, so you can see that, okay, these are influenced by factor 2 here. These are influenced by factor 1 here. Okay, this is much better than here. Yeah, so in this case, you can have orthogonal rotation. So original one, we have orthogonal axis, y-axis here, and then you can just change the different degrees, angles, or put different center here. But here, it's oblique. Okay, so for this new axis, they are not orthogonal anymore. Okay, so this is the degree is not 90 degrees. So you can also use optical rotations to help understanding the result of the vector scores. So let's look at some type of rotation methods. For example, yeah, just look at these rotations. I give you some verbal description here, but actually these are decided by some mathematical forms. I didn't include those mathematical forms. Okay, just show you the concept here. Varimax is orthogonal method, orthogonal rotation method. So orthogonal, what does that mean? Orthogonal. So the factors, the correlation between factors are 0. Okay, so there's no correlation among factors. It's orthogonal, independent, uncorrelated. Okay, orthogonal. So what is this method? It tries to maximize the variance of the factor loadings. Okay, so we have each factor loadings, we have variance. We try to maximize the variance of the factor loadings. So what is aim? Aim for a simple solution that each vector has a small number of large loadings and a large number of zero loadings, or close to zero, or very small loadings. Then we try to extract some vectors which make the solutions very simple, and each vector has a small number of large loadings. Okay? So some vectors has really large numbers, but the other numbers, loadings are very small. So that is the goal. Trying to do the very max. Okay. Why it's very max? It's a variance. Okay, variance max. Okay, maximize the variance of the vector loadings. Very max is orthogonal. We can also do the Promax rotation. For this rotation oblique, it's not orthogonal. Okay, so this way, vectors are allowed to correlate. Okay, the degrees between vectors are not 90 degrees. Okay, so the correlation is not zero anymore. We have some correlations among vectors oblique. They try to fit a target matrix which has a simple structure, and we have two steps. In the first step, we're gonna define the target matrix. Okay, almost always obtained as a result of varimax rotation. So from the first method, varimax rotation, okay, whose entries are raised to some power. Okay, so from the first varimax rotation, and then we raise the power, for example, to 2, 3, 4. Okay, we have a new target matrix. And then conduct the least square fit from the varimax solution to the target matrix. Okay. Two steps. We can also have a geomean rotation. It's another type of oblique rotation. It's default in M plus. Okay, M plus. Think that this method is the best one. Actually, yeah, it can be seen. It can be treated as the best rotation method. We can do the comparison. We try to minimize the geometric mean of squared vector loadings. So that's why it's called the geomean. Geomean, okay. Geometric means of squared vector loadings. And then that is a minimized. So this is a geomean notation. So that's a theoretical part. In our code, R code or M plus code, okay, so we can just use different options. We have some options. If you change the option, then the rotation method will be different. It's very simple. Okay. This is the background. Okay, that's 3 types of rotation. Of course, we have a bunch of them. Okay, I didn't do the introduction to all of these. Okay. These are very popular methods. Any question? Anyway, the goal is trying to help to understand the vector scores. Okay, trying to provide a better interpretation of the data. So you can try different methods, locations. Okay, if you don't have any question, then we're gonna move forward to vector scores. Okay, vector scores. So sometimes we do need to obtain those vector scores. Shows, okay, what is the score of those latent vectors? And we have different methods. One way is called the regression methods. So once we have the lambda estimation, okay, we can use this method. It's called regression. So lambda, the transpose of lambda, all of these are obtained from the previous estimation. So and the lambda, transpose of lambda plus psi, and the whole matrix here, inverse, and the y observed. And this is one method to get the vector score. You can also use a Bartlett method. So the transpose of lambda, psi, inverse, okay, all of these again is obtained from the previous estimation. inverse of psi times the lambda and the whole product inverse times the transpose of lambda inverse of the psi n times 1. So finally, these are vectors because we have vector scores for each individual and for each factors. Okay, so we have this method. So you can just do the exercise. Yeah, in the second session is our code example. So you can just use a different estimation method to obtain the scores. But, okay, so you can do that, but this actually is not recommended. Because these scores do not correspond to true factor scores. As I mentioned, actually factor scores are not unique. So what you obtained by using these methods are not true factor scores. So it's kind of risky, okay? It's quite risky to obtain factor score as estimates first. But some people just do that, okay? You run the factor scores and then based on those factor scores, conduct a further data analysis. Okay? This is kind of risky. Okay? So first step, order the factor score estimates and then conduct a further analysis on them. And even more unjustified to interpret the factor scores estimates for specific individuals. So people think that this is not a very good way to do that. And we have some papers talking about the details of factor scores. If you really want to do address the question about relationship, then you can just by looking at the whole SEM, the whole structural equation modeling. Okay, not specifically look at those factor scores for each individual. You can generally look at the whole structure, so whole structural equation models and do the explanation, not for each individual scores. So in general, people suggest that should avoid, okay, researchers using the factor analysis should avoid situations involving estimation of factor scores. Actually, last semester, some people finished the course project. Okay, although I mentioned that it's better to use observed variables to not involve the factor scores, but factor models, but still, there are some papers talking about factor analysis. That's good, okay? But they also trying to extract those scores and do further analysis based on those scores. So those are advice. People actually don't recommend it that way. It's not quite good. Those are not true scores. Okay, the final goal, we're gonna do the interpretation. So we need to, after we got the whole lambda matrix, okay, we have a lot of lambda loadings. We're going to identify significant loadings. If the loading is really close to 0, sometimes, okay, people think the cutoff point is 0.3. Some people suggest 0.2. Okay, if the loading is less than those numbers, we can just totally ignore them. Okay, and then find the clear pattern. The last step, we're gonna name those factors by looking at the meanings of those items. Okay, you're gonna figure out the meaning of these factors. So what does that mean? Okay, so we have some group of items together. So what is this group for? Okay, so we are trying to measure same factors. So what is the name of the underlying factor? So you should give a name. Similar items. Okay, so that's for the introduction to the EFA. We just trying to finish the goals, trying to do decide the cake. Okay, we're trying to decide the cake, and then we're trying to do the estimation, okay, for how to figure out the lambda value, psi value, and then factor loadings, and then we're gonna do the interpretations. So these are our goals for EFA. So in the very beginning, yeah, so we're trying to decide how to figure out, okay, how to, to determine the K here, how to decide the number of common factors, how to decide the strength of the relationship, mainly, okay, get the lambda here, and how to do the interpretation, okay. Yeah, so we introduced all of these topics. Any question? Any question?
Yeah, the ProMax and the VariMax, do people tend to do both at the and then just kind of
You can try many of them. There are a lot of options actually in R, so you're gonna check the code. They provide a lot of rotations. You're gonna see which one provides the best interpretation. Then you're gonna pick that one. Sometimes maybe VariMax can give you a very clear pattern of the factor structure. For example, 1, 2, 3 item. Okay, item 1, item 2 can be influenced by one factor. 4, 5, 6 items, okay, can be influenced by another factor. If you can see a very clear pattern, you can just start there because you have your way to do the interpretation. But sometimes it's not very clear. You're gonna try method 1, okay, rotation 1, rotation 2, rotation 3, rotation 4, and then pick the best one. Sometimes even you tried all of these rotations, but the pattern is still not very clear. Then you're gonna think about, okay, is that due to my questionnaire? Because I didn't explain that item very clear. So people just don't answer that item very well. So you're gonna delete some items. Or yeah, I would tell you there are a lot of tricks. Yeah, so or you can delete one factor, or you can delete some items to make the whole the pattern structure best. Yeah, of course. It's up to you. It also, you're gonna look at your literature because some people might give you some background of the design. Okay, so you're gonna look at the data and also you're gonna look at the research papers and decide your factor pattern. Yeah. Any other question? Yeah.
To what extent, I guess maybe I'm not quite clear about this, but are the different rotations like mathematically equivalent?
No. They are not mathematically equivalent.
Okay.
They have their own mathematical equations.
So in that case, how does this idea of fitting multiple rotations, does it present an issue?
For example, if you look at this case, it's very obvious. Okay, suppose in this case, so for example, for example here, if you change the angles, the theta here, you will have different rotation. So, but finally, you're gonna find something, okay, which can best explain this part of data, this part of data. So you can think, okay, the green dots are influenced by one latent factor. The blue dots are influenced by another latent factor. If you change the axis to another angles, you can still do that, but maybe it's not good way to do the interpretation.
I guess I was wondering what kind of problems does this present when you haven't, for example, theoretical rotation you're going to use. There's no theoretical basis for what rotation you're going to use. And does it present a problem with a garden of working paths and statistical analysis?
That's a good question. Yeah. So if you don't have any theoretical guidance, if you don't have any previous research, then you're gonna figure out, okay, is this item truly correlated with that item? Is that truly influenced by that factor, underlying factor, or is this item influenced by both factors, or yeah, it's combination of several factors. You're gonna think about that. But the data or the numbers, I will give you an example. The numbers will tell you, okay, maybe this one is influenced by that factor, not influenced by this factor. You're gonna check those numbers. Yeah. I'm sorry, this is too abstract because we don't have any actual data. We don't have the detailed the explanation. So we will have example and which will help us to understand the whole procedure. Yeah. Any other question? Good. Then let's have a break and 15 minutes break. And at 7, we can come back and we're gonna look at the example. Okay. Of course, we're gonna also talk about some practical issues. For example, how to decide your sample size or some other issues. And then we have the code. Okay. I will give you the data set and also I will give you the code of R code, M plus code, how to do the data analysis. Okay. How to conduct the EFA. Okay. Yeah. Thank you. Yeah. Questions? Yeah.
So in an environmental.
Yeah.
All the good stuff.
It's good to share your story.
Well, it's nice having so many, therapists in the room.
Therapy has been awesome.
She's not just in marketing. You're marketing, right?
Me? Yeah, I'm communication.
Communication.
Yeah,
Sorry.
so.
Yeah.
Some things. Yeah. So I'm in clinical psych and he's in counseling psych.
Yeah. And I'm in need.
Yeah.
Go ahead, Dr. Liu.
Okay, yeah, let's look at some practical issues, okay, related to EFA. For example, how to choose those observed variables or indicators. So when we design our test or items, okay, so we're gonna collect some items. We're gonna get some items that has been carefully developed to measure certain domains, not just random items. Okay, so when you choose those indicators or test items, okay, we're gonna carefully look at those item meaning, okay, not just random variables. And the number of factors can be influenced by the number of variables per factor. So yeah, you will see that if you change these numbers, it will be different. And you can, okay, sometimes, okay, so in some cases, you may have, like this case, we have one factor here, and then you have a lot of like items or indicators. We sometimes call that indicators, or in practice, it's just items or questions, tests. Sometimes we may have a lot. And some factors, for example, at 2, we only have 2. This is actually not very good design. You can try to make the structures quite like balanced. So for example, here, there are so many items are trying to measure the same factor, 1 here. But here we only have 2. Sometimes even you only have 1, okay? So we have 3. Sometimes you can just have 1 item. In this case, this is definitely not well designed, not good case. You don't need to have 1 factor if you just have 1 item, okay? But sometimes 2 is still acceptable, but 3 to 4 is kind of like the best. So here we have too many, okay? So we can sometimes have more. This is, of course, is not very good pattern. So we can try to make similar number of variables per factor. Yeah, at least 4 or 5 variables per factor is recommended. Okay, so 3 or 4 or 5, yeah, that's good. If you have too many, it's not good. Okay, if you have 1 or 2, also not good. But 2, in some cases, people said it's still acceptable. Okay, 3, 4, 5, that's good.
So in a survey, these variables would be our constructs that would be measured, like 3 or 4 different constructs or questions to measure that item.
when you start the design the questionnaire, you have some idea. Okay, so these items maybe can measure something. So in the very beginning, so you can have this structure. Don't use too many items to measure some same vector. And some vectors can be just measured by 1 or 2 items. That's not very good case.
But if other literature, like historically, this model has always had these 2 questions.
Yeah, that's very
Or
common.
2
That's very
constructs.
common
Okay.
because sometimes I read the people's articles, so more than 10 items just measure 1 vector. So theoretically, that's not the case, but because in that traditional test or traditional area, so they just do it all the time. So you can still use that, but if you're trying to simplify, okay, you can just pick some really good items to do that. That will be best. Don't
So-
do all of these. Yeah.
When we write it up, if it's only 2 items measuring or 2 constructs measuring
It's
things,
acceptable,
should
but
we
it's
write
not
it
good.
in there? But should we say it? Traditionally, this is only measured with 2.
You can do that,
Okay,
but definitely not just 1. This is not good. Yeah,
Sure.
Yeah.
okay.
Yeah. So if you have so many items, I suggest you to just pick 4
Key
3.
ones.
Yeah. Don't need to do all of these. Yeah. Okay, now let's look at sample size. One rule that, okay, the sample size should be larger than the number of parameters, okay? So let's look at this case. Suppose we have 5 vectors. Okay, so let's do the calculation here and trying to figure out the sample size if you have the similar vector structure like this. Okay, so if you have 5 vectors, each vector with 5 items, okay, that's good, okay? Each vector, 5 items, 5 indicators, and you have 5 vectors. Then, okay, let me ask you, what is K in this case? If you have this vector model, what is K? What is the capital K?
25.
Factor K, the K, capital K.
Oh.
What is the number of factors for K in this case? In this case, what is the capital K? Yes, good, okay. Then what is P? What is P? What is P?
3. It's always said it's 1.
What is
Sorry,
P?
125.
P is number of variables, number of items.
25.
Exactly. Okay, good. In this case, we have 25 items. We try to measure 5 latent factors. Now, what's the total number of parameters? We have formula. The sample size should be larger than the number of factors. So what is number of factors in this case? Remember, what is the number of factors? I'm sorry, number of parameters. Number of parameters. Number of parameters. We have formula, okay?
PK plus
Yeah.
K.
Well, we have P times K plus K times K plus 1 divided by 2 plus P minus K squared. So P, okay, we have P 25 times K 5 plus K is 5 times 6 divided by 2 plus P 25 minus K 5 squared. Okay. So we have, wait a minute. So here we have 5 squared, okay. 5 squared, so we have, this is just done, okay. So that's why we have 140. Yeah. So if you have this case, 5 vectors, 25 in the items or indicators, the number of parameters is 140. number of parameters, you want to estimate those parameters, you have 140, that's a lot, okay? So at least the sample size should have 140. Okay, based on this rule, the sample size is better larger than the number of parameters. This is just one rule. But also people think that you can also follow this rule. Several observations per parameter. Suppose if you want two observations per parameter, number of parameters is 140. If you want to have two observations or a two for each of these parameters, then you should, like Lisa, you should have 280. Okay. And of course, if you want to make sure the sample size is larger, suppose you want to have 3 observations per parameter, then you're gonna times 3 of this number. Okay. This is another rule. Okay. Some people also have this rule. Okay, so minimum 10 observations for each variable. In this case, okay, how many variables? For each variable, how many variables? We have 25 variables, okay? And if you follow this rule, okay, minimum 10 observations. So you need to have sample size 250. Okay, of course, those are minimum. The larger the better. If you have time, you have energy, you have budget, you're gonna collect more. But these are minimal, okay? At least you should have this sample size. Of course, we have different, rules, okay? So if you're gonna follow this rule, then 150 is the minimum, okay? If you have 2 observations per parameter, then 280. If you have, if you're gonna follow this rule, then at least 250. That's all for this case, okay? Of course, if you have different, if you have different models, this is only for factor models. If you're gonna consider some other variables, then you're gonna increase the sample size. This is a very simple case. If it's just factor models, okay? Then we have some suggestions for you. There's no absolute number, okay, absolute sample size, which one is correct, which one is wrong. There's no suggestion, okay. Well, we have some rules, okay. Okay, then let's look at the other issue, size of factor loadings. So factor loadings, it could be really large, it could be really small. For example, close to 0, okay? So that tells us the relationship between the factor and observed variables. Okay. So sometimes, if it's really small, it's not significant, okay? Then we can just ignore that. It's really close to 0. Sometimes, if it's significant, but for example, the value is not quite a lot, then still we can just delete that. We can drop that. And when we develop some tests, okay, you're gonna after you get some factor loadings, you're gonna look at those items again. So you can just remove variables that poorly measure factors. Okay, delete items with cross loadings, as I mentioned. We're trying to find a very clear pattern. Okay, we're trying to find some patterns like. We have some items here, and we have some factors, influence, and factor cross-loading. What is cross-loading? Okay, for example, this item 2, it is influenced by factor 1 and also influenced by factor 2. Sometimes also influenced by factor 3. Okay. So we call this cross-loading. So this item is influenced by so many factors. It's not solely designed for F1. So we think that this item maybe it's not good. Okay. we hope that an item can measure the same, the solid factor. This is better. Of course, this is allowed. Sometimes we do need to use items to measure some factors, but this is not ideal case. You can just delete items with cross loadings. We hope that we have very clear, very simple pattern without any cross loadings. So this item might be removed. Okay. And then you can also remove factors that are poorly measured. Delete the factors with only one or two items, as I mentioned. Okay, sometimes, okay, so you have factor one, it only influence some item, okay, just one item. This factor should be deleted. Okay. This is not necessary to extract a factor just based on one item. And sometimes you have two items, okay, items. So some people say, okay, this is also not good factor. But yeah, there's some argument. Okay, people think, okay, maybe two items is still acceptable. Okay, one or two items. So you decide. You decide if you're gonna keep this item, keep this factor, or delete this factor. And if you have cross loadings, you're gonna decide if you're gonna keep this item or not. If this is a very, very important item, you cannot remove this one. Then just leave the cross loading here and do some explanation. Okay, so its item can be influenced by some common factors together. Okay, but it's always not very good case. So these are some issues when you develop your items. You can just think about these suggestions. Yeah, for sure.
So is with this, what you're showing us, it would be better to do a sample survey of a smaller population before you to test all of these variables before you do your huge data collection. Is that what, because you have to have data in order to measure these variables. In order to do that, you need a smaller sample size, correct?
Sample size always larger the better.
Well, but
You're
I'm,
gonna focus on the correct target population. If you have really good population, the samples can really, it's very good candidates of the whole population.
well, the reason I ask is because I'm thinking of doing a small 50-person sample before so I can do my validity and all that on my model before I go and collect the 1,000 that we're looking at for the overall. So to test all this.
Make the factor structure simple.
Okay.
Don't try to measure a lot of factors.
Right.
From small.
I'm lazy. It's going to be as easy as possible.
Okay. Yeah. Okay. That's good. Okay. Yeah. Thank you.
Thank you, man.
Yeah. Okay. Now we have already prepared so many knowledge that we can just apply that those what we have learned to this example. So this is also very famous example. We're gonna use it a lot. We use it previously and other data analysis. So we can just call it the Hosinger or Hosinger. It's the last name of the people. Hosinger. How to pronounce it?
You're doing as good as I am.
Hosinger maybe okay. So it's very old, traditional data. So a lot of people just use it for data analysis. In total, there are 26 tests. These tests are trying to measure a general factor and find specific factors. Okay, and collected from 7th and 8th grade students in 2 schools. Okay, GW school and the PS school. Okay, the Pasteur school and the Grand Wide school. So we have sample size and total is we have around 300. Okay. So these data are for analysis including. So this is the total general, the general introduction of the total data set. Okay, we're trying to get 19 tests. Okay, from 26 tests, we're trying to get 19 tests, and we're trying to measure these 4 domains. Okay, so for 26, we have 5 specific factors, but we just extract the subset: spatial ability, verbal ability, speed, memory ability. Okay, and we just use the sub sample from GW school. Okay. 145, I'm sorry. So that's a subset from the whole set. So let's look at those tests. Spatial tests, this is one cognitive ability we want to measure from the students. And they have 4. Spatial ability can be tested by this, can be tested by these 4 subtests. Okay, so visual perception, and the cubes, paper form, board, okay, and lozenges, how to pronounce this word?
Lozenges.
Lozenges, thank you, yeah, lozenges, okay, lozenges. And the verbal ability can be obtained by looking at these 5 tests. That's spatial, okay, spatial. This is verbal. General information, paragraph comprehension, and the sentence completion, word classification, word meaning. Those 5 tests are trying to get the verbal ability. And the speed test, okay, add, code, counting groups of dots, okay, straight and curved capitals. Okay, those 4 tests are trying to measure the speed ability. And here we have 6 tests, okay? We're trying to measure the students' memory ability. Word recognition, number recognition, figure recognition, object number, number figure, figure word, okay? So here we have 10 tests in total. Here we have 9 tests. In total, we have 19 tests trying to get these 4 abilities. So I give you the code. If you go to ELC, it's called housing text. Okay, so download the housing text and also the R code. Download the data set and the code and save to your local folder. And then we can just try to do the exercise. Okay, so we have, we have our code here. Let me just start from the very beginning, okay, to show you how to do. Oh, in the search box, so trying to type R Studio, and then open the R Studio. Okay, so you gonna, okay, suppose you have already saved your code, then click File and Open File. Open your R code file, okay, so go to your folder and then pick the code. It's called EFA housing 2022, okay, R.R. And then that's it, okay. In the very beginning, I said working directly. Okay, so basically, if you want to use this command, you're gonna fill out the test information here. So where's your data set? Okay, this tell us your test. But you can also click session. Okay, so if you click session, click set working directly. Okay, so you're gonna manually set working directly from these items. The third one is choose directly. Okay, choose directly. And then you're gonna tell R Studio where's your data file. Okay, so just choose those folders and suppose this is your folder. Then here automatically tells R that this is my test. Okay, I have this and this is my test. And the data file is saved in this folder. So if you try to manually write this command, then you're gonna complete this sentence and just like this, and highlight this part and click run here. Okay. Now you're gonna read data into R. So we have already learned this command. Okay, read the table, read the dot table. Because this is text file, you don't need to have any special package. If you have a SPSS or other Excel file, you're gonna read the foreign package. Okay, remember we have a lot of package and read different types of data into R. If it's text file, the housing is a text file, you can just directly use read table and tell R, this is your data file. And if you check the data file, okay, let me show you the data file here. Sorry, what this is. So we have so many columns, okay, so many variables. ID, female or male, okay, grade, and age, school, visual, cubes, paper, okay, a lot of tests, okay, all of these are tests. The first row is column information or the variable names. So header means a table header, okay, so if in your data set, if there's a column names, you should tell R that we have the header included. So header equals true. And then you saved everything into this object. So in R, the data set is called housing. You can use head, just take the first 5 rows to check the information of the data set. Okay, you can just use head to check the data set. You can highlight this part and click run. That's it. So you have so many columns. Okay, the first 6 rows are shown. And the output, this is output panel, this is the input panel, this is also the background information, the data file, data information. And you're gonna take some tests. We are not going to use all of these, okay, because we have ID, we have female, we have grade, we have so many columns. Remember that in the first semester, in the SEM1, we have some R code. We pick some variables.
Combined.
Yeah, we pick visual, cubes, paper, 19. There are 19 tests only. I'm gonna use 19 tests only. So all of these are called, okay, I'm gonna use it for factor analysis. Factor variable, this is just a name. Okay, you can just change the name. It doesn't matter. You can change my factor model or my factor data, whatever. It's just a name. And then from the original data set, you pick those columns only. Brackets, remember brackets, we have 2 parts of information. The first part is row information. Second part is column information. Column information is defined here. So I'm gonna pick all of these columns only. And the row information is blank because all rows are included. I'm gonna use all rows, okay? And with these columns only. So this is the data extraction. If you remember that we extract the smaller set of the data from the housing data. The FA data is, okay, so the FA data is quite small. And you can also check that, okay? You can use head to check the simplified data, okay? So you can highlight this part and click run. Okay, now I only have 19 tests. This is a factor analysis data, simplified, small sample size, smaller columns. Okay. Yeah. We don't have ID, we don't have gender, we don't have grade information. Smaller subset. And you can also check the dimension, how many columns, how many rows by using this command, okay? And column, number of columns, how many columns? It should return 19, I'm sorry. It should return 19 because we only have 19 tests. Okay, highlight, click run, 19. How many rows? Okay, how many rows? Let's check. What's the sample size? 145, okay, because we just use a GW school data. And you can also look at the correlation matrix. Okay, so COR means correlation matrix of these 19 variables. So the outcome of this will be 19 by 19 because here we have 19 factors, 19, I'm sorry, not 19 factors, 19 tests, 19 variables, 19 items, okay? So 19 by 19 is a factor correlation. So highlight, run, it's huge, okay? It's huge, 19 by 19. Very big Forest matrix. And then, okay, now let's look at that. Eigen decomposition. Eigen decomposition is our focus. How are we going to do that in R? That's it. Eigen, that's it. Eigen. Inside this eigen is our correlation matrix because we try to do the eigen decomposition for the correlation matrix of the data set. We just obtain the correlation matrix here. Okay, correlation. This is a correlation matrix. 19 by 19, 19 by 19 here. If you just type in eigen, it will do the eigen decomposition for you. So the eigenvalues, eigenvectors, all the information will be obtained here. So we save all the results into this object. It's called factor analysis eigen. Again, this is my name. You can just change it to name, okay? For example, eigen decomposition, so whatever. You can check the names, okay? Inside of this object, we have some eigenvalues, and eigenvectors. So by using names, you can just check values and vectors. Let me ask you, how many eigenvalues do we have in this case? How many eigenvalues? How many eigenvalues?
19.
Exactly, because we have 19 variables. From the biggest one to the smallest one, in total, we have 19 eigenvalues. Of course, we have 19 eigenvectors, okay, if it's orthogonal. So let's just try to do that.
So can I ask a question?
Yeah.
So when you're wanting us to define each one of these lines of codes for the homework 2, are you wanting us to go in as depth as you're explaining it now or more brief?
I just want you to understand the code because later on, this will be your
Correct.
EFA. So I want you fully understand each command here.
Okay.
So that's your homework 2. Okay, homework 2, just do the explanation of this code. Yeah, because for homework 3, you will have actually do your homework EFA.
Right.
So eigen means, okay, do the eigen decomposition. Yeah.
Okay. Thank you.
Good. So actually, I'm just doing the homework 2 for you.
Correct. That's why I was asking. That's why I was asking.
Okay. Okay. So let's try to run this part. Okay, do the eigen.
Good thing I got it recorded.
Okay, names, let's check. Now, what's inside this part, okay? We have 2 parts. We have eigenvalues, we have eigenvectors. And remember in SEM1, we can use a dollar sign to take the specific part of the outcome, okay? So dollar sign value, let's check the eigenvalues, 19 eigenvalues of this correlation. That's it, okay? Eigenvalues from the largest one, 6.3 and 1.9, okay? And then this is smallest one. In total, we have 19. So, okay, this is 16, 17, 18. Okay. And we also have 19 eigenvectors. So for each eigenvectors, we have 19 elements. Okay, highlight and do that. Okay, so you have 19 eigenvectors. So this is the first eigenvector. Okay, so it's a vector. It's 19 by 1. So we have 19 elements. First element here, okay, yeah, from here to 19. One vector, second vector. The second vector is associated with the second eigenvalue. So it's one, yeah, it's 1 by 1 corresponding, okay? This is the largest one corresponding to the eigenvector 1 here, okay? The second largest one, 1.9 is corresponding to this second column, okay? So one number and one column here. All of these are available for you. Nice. And then you can check, okay? You can plot. Before we do the plot, let me ask you, okay, based on the eigenvalues here, if you use Kaiser's rule, how many factors are you going to extract? If you use Kaiser's rule, remember what's Kaiser's rule? If you follow Kaiser's rule, how many factors?
4,
Why?
because they're above 1.
Exactly. The first one, larger than 1. The second one, larger than 1. Third one, larger than 1. Fourth one, still larger than 1. Stop here. Because now this one is smaller than 1. So based on Kaiser's rule, the capital K is 4. The capital K is 4, okay? And then let's plot. If we use a script, plot. Then, okay, so plot is another function. It's very, very powerful in R. If you use plot, there are a lot of options you can check. Yeah, if you don't know how to use a plot, question mark, plot. So this area, we show you the details of the plot. Let's just try to look at that. Plot, okay, run. Oh, okay, so we have different base. If you just look at the base. So this is a default scatter plot function, the plot, okay? So we have all of these options. Okay, so this is the details of function, how to use that. Okay, a lot of parameters, a lot of options, a lot of settings. You can just read the manual here. And then also we have a lot of examples, show you how to run the plot. By the way, if we just want to use the plot, what does that mean? Okay, I'm gonna show the plot of these eigenvalues, 19 eigenvalues. Type, let's look at the type. I give you different options. Okay, the same plot, but different types. This tells us what's the type of the plot, okay? It could be line, it could be point, it could be both. Let's check the difference among them. So if it's both, that means the point and the lines will be shown in the plot. Let's do that. Highlight and then run. That's it. This is our 19 eigenvalues. Largest one, second largest one, third one, fourth one, and we have a lot of that smallest one. If you count, it's 19. And the B means both. I have some dots, I have some lines, it's both. If you change the type to points, I only have dots, I only have points only without any lines. If I have L, then I only have line without any dots. Okay, so just check the difference. Plot P, plot P only. That's it. These are 19 dots, 19 points, just points without the connection lines. Okay, connecting lines. If you want to show the lines only, use this one, and that's it. There's no points, no dots, just connecting lines. Okay, so again, here you can change all of these types. There are a lot of options for you. All of these things will be described in the plot, okay, in the functional plot. Okay, so let's try to run the both. Okay, again. Based on this plot, okay, based on Kaiser's rule again, so this is one here. We have 4 vectors, case 4. If you check the split plot, okay, split plot, again, you have 4 here, because from here to here, they are so similar, these dots are so similar, so we just stop here. Okay. So we have 4. And if you want to do parallel analysis, okay, this is the code for parallel analysis. Parallel analysis, let me explain this part, okay? So this is called the function, okay, from here to here. From here to here, the whole block. So if you want to run a function, you have to highlight the whole block and then click run. Because the whole, from here to here, let me show you, okay, so from the function brackets, okay, to the end of this bracket, this is one function. This is one function. Function is a name. Okay, you cannot change anything here. It's just function. And inside the function, you have the data. This is the original data. And this tells us, okay, you're gonna repeat how many times? Okay, so you're gonna repeat 1,000 times or 2,000 times. Percent. What's your up bound? Okay, so you're gonna use a 95% up bound or yeah, whatever percent. So this is a function. We have 3 pieces of information, and after you run this function, you can use this function. This name is called SEM parallel analysis. Okay, this is the actual data set. This is your repeated number. This is a percentage. Okay, up bound percent. You can change this information when you call that function. That function is kind of like it's a function. It's built by the code. Okay. Every time you call that function, this is the name. When you type this name, you just call that function, and then you input the information into these positions. Based on a different information you input, the outcome will be different. Okay. So this is just the function. So you just here you write the function called SEM parallel. Let's look at the inside of the function. Let me make it a lot of it. So from here to here, it's original eigenvalue. Okay. So the logic, remember the logic, we compare the original eigenvalue with the average of the noise with eigenvalues. So from here to here, it's original eigenvalue calculation. We got the eigenfunction. Okay, eigenfunction to do the eigendecomposition. But what is the correlation matrix here? Okay, correlation of the function. The function is the information. Okay, this suppose this is the information input. Okay, this suppose the information you input. So the data here, the data value here, correlation. The correlation matrix here do the decomposition. Okay, eigen decomposition of the correlation of the data set you input. And then you pick the eigenvalues. Okay, use a $sign, pick the eigenvalues. And that is the original eigenvalues. Okay, original eigenvalues are saved here. And this is a rows, number of rows of your data information. How many rows, sample size, and here. Number of columns of your information you just input. Okay, how many columns, P here. From here to here, I'm gonna create a matrix to save all the repeated generated data. Originally, I create an array called null. Okay, nothing, it's empty. The name is called parallel analysis eigenvalues. Okay, and then I start from 1 to the repeated number. The R should be very large here. Okay, the R could be 1,000, 2,000. So from 1 to the repetition number here, I just do the loop. This is a loop. This is a for loop. Okay, I just repeat R times from the first time, and the semicolon. Okay, column here means okay from 1 to R repeated times. Okay, and R is from all of these arrays. So I'm gonna repeat R times. And for each time, for each loop, what is inside? For each loop, I'm gonna generate a data set with the same size and rows, p columns, with the same dimension of the original data set. Okay, the original data set have the n rows, p columns, that is dimension. So I'm gonna generate R norm. What does that mean? R norms. Random data from normal distribution. Random data from normal distribution. What's the dimension? N by P. Okay. So I just generated those numbers, and we have n rows, p columns. Okay, this is the dimension of the array. Okay, these are data. And I have n rows, p columns. So finally, I created array. Okay, array is kind of like a matrix. Okay, it's kind of like a matrix. And the name is called temporary, because every time I'm gonna replace this data set and renew it. So this array is called temp. By the temp, I'm gonna carry the correlation of the newly generated temporary data set. Do the icon decomposition. The icon decomposition was saved to the temp icon value. Okay, and the temp icon value, I take out the values. I take out the icon values only, and I save the two icon value matrix. And I use rbind to put all of this together. Okay, rbind. I just save all of this together. Okay. So we have one R could be large. Okay, so suppose 1,000. I have 1,000 rows of the icon values. Every time I just add one row. Okay, I just add one piece of information. So here, from here to here, it's a loop. It's for loop. It's a loop. I created R rows of icon values. Next, I'm gonna calculate the average. How? This is another function, very powerful function. It's called apply in R. Okay. So I'm gonna apply. Calculate the average, okay, mean average of this matrix, this whole matrix, to its column. Okay, wait a minute. We have row. Okay, so we're gonna check the apply. So if you want to check the details of the yeah, so this is a detailed explanation of the apply. So we have different margin values. Okay. So we have 1 indicates rows. Okay. 2 indicates columns. So I have 2 column means for each column, because I have so many rows. For each column, I calculate the average. So the largest one average, the second largest one average. So based on column. Based on column 2 indicated columns, and get the average of all these icon values. And that icon value is called mean of icon value. I name it M, mean of icon value. I also calculate the up percentile, okay, 95%, okay, it depends on you, so the percentage, suppose is 95%, then the probability is percentage, this information you want to input when you call it. You're gonna calculate the quantile of that value. Again, it's 2 means indicated as the column. By column, you calculate the quantile of all of these eigenvalues, okay? And you call it a P, okay, it's percentile eigenvalues. So you have 2 pieces of information here. Now you're gonna plot the eigenvalues. This is the original data eigenvalues, okay? And type B. And you can change the X label and the Y label. X label is number of factors, okay. The Y label is eigenvalues. Yeah, it just tell us the meaning of the X and Y labels. And then you add some lines, okay? Add some lines. What is lines? Average of eigenvalues. Percentile of these eigenvalues. And here you can see that I have LTY. What is that? Line type. I have different line type. Line type is 1, it's solid line. Line type 2 is, let me see, 3 is dotted one, 2 is dashed one. Okay, so we have different types of the line. You change the name here, you will change the line type. Because that is a plot, you can also add a legend, the legend. Where's this position? Where are you gonna put your legend? Top right, okay? Top right. And we have some explanation of this legend. I have the actual data plot, I have the average plot, I also have the percentage, okay, the percentage. But this part is too detailed. If you don't understand, that's okay, because you can just copy this part and you apply, just call this part, okay? But this part is too tricky. It's tricky because you take the information from the input function and then you add the percentage. You also use this separate symbol to connect them. And the line type, okay, different line types. So this is for legend. And also, yeah, we have some other information. So you can just highlight all of this function, highlight the whole block and run. This created the SEM parallel analysis. Sorry, this created the SEM parallel function. When you actually use it, just call it, okay? And this is the actual data, factor analysis data, FA data. I'm gonna repeat 1,000 times, percentile, 95%. This is the actual information you're trying to use that function. I'm sorry, now it's 8. We cannot finish this part. So we will continue the next time. Let's try to run it. Okay, so you will have some plot here, because when you call it, you use a plot. It just shows you the plot here. So highlight and run. That's it. This is actually the plot we use in you see the slides. So that's it. We have legend. This is the legend. Top right. We have 3 parts of information. We have data file. We have actual original data, average 95%. And we have the dotted line. We have 2 average line, the percentile to show the parallel analysis. You can change it a lot. Okay, you can change this function. For example, you can change it original. This is original data. We can also top left. Then this part will be covered. Okay, the first dot will be. That's not good. Okay, this is good. Okay, this is top right is good. So if you, or you can change the average to mean. So yeah, You can just change to everything. It's average, it's mean.
Every time I do a graph, it seems like I always fight with that margin and all that right there, the most
Yeah,
and
you can, yeah, you
the
can change
legend.
something here, yeah. In that case, it's original data, yeah, and then you
Sure.
have mean, yeah. Also, you can choose the line type or, yeah, whatever. Color, you can also put color, you put the color, okay, yeah. Let's just stop here because now is 8:02. Okay, next time we're gonna continue the R code and the homework 2. Yeah, a lot of you have already read the homework 2. Just do the explanation of the code. But for the parallel analysis, if you skip this part, it's okay, because actually it involves some very detailed, tricky parts. So, but you have to understand the main idea of this function. Okay. And yeah, we're gonna continue the factor analysis. For example, here, the rotations. Now, okay, in the very beginning, I didn't do any rotation. Rotation, varimax, okay, rotation max. You can just change the option here. Number of factors, okay, 4, because we have already decided the number factor is 4. So number of factors 4, 4, 4, okay, the data here. And factor scores, you use different methods, yeah. Let's continue next Monday. So today we don't have any homework. So because we haven't finished this part.
Oh, cool.
So next Valentine's Day. No homework.
That's better than any chocolate.
So yeah, next week we're gonna finish this part and we will have CFA, okay, confirmative factor analysis. Okay, and the homework 2 will be after the explanation. Yeah.
But with how many lines of code that is, I'm going to start on it this week anyway.
Okay.
That's a lot of lines.
That's good, yeah. Okay, so that's for Yafei today. Any question? Question?
This kit contains registered map test, the map test,
What is a map test?
MAP.
Map,
Yes,
map test?
yes. It is like similar parallelize to decide the factors.
I feel like this is gonna
Okay.
like break my heart though. So who sent
So-
this to you?
So my daughter did. So
Oh,
I
your daughter
started.
sent this to you.
So I started off by telling her, "Hey, have a happy Valentine's Day and all
Oh, this
this."
is today.
This was this morning,
Okay.
7:30. She says, "Okay, I won't." I'm like, so I'm sitting in bed. I'm like, great, she's depressed. I'm like, oh, the boys will love your hair because we just got it done, you know. And I asked her, "Did you brush it? Does it look nice?"
And this is the one who got the haircut. Okay.
Right. And she says, "Yeah, but no losers for me." I'm like, okay, so I'm trying to get her, you know. And I'd given her a whole bunch of eggshells to her ag teacher for their garden.
Oh.
But she says, I didn't ask for it. She's like, "I'm going to send you a video what Skylar does every morning." Okay. And
Oh,
she
it's
even
every
says,
morning.
yeah, she says, even on her birthday, which was just a couple weeks ago.
Oh.
So let me turn this up and listen to this. Take it.
This is why I wish